some of it's a review of thermochemistry. Some of it's added new information about thermochemistry. There's some graph reading and other things you'll notice in this particular PowerPoint. So thermochemistry, of course, the metric SI unit is joule for heat. We will be using heat a lot here. Energy, thermo energy is heat. The non-SI unit is calories, of course, and you do need to kind of know these values. 1 calorie equals 4.184 joules. Although, you know, that's in tables and things, you're always welcome to look up and use your notes, of course. So conversions, very simply put, 425 joules. You guys know how to convert at this point. So 4.184 joules equals 1 calorie, and you calculate it, so forth here. Set up the T-chart, 275 calories, 1 calorie equals 4.184 joules. It's just the opposite. This one has 3 sig figs, this one has 3 sig figs. So we're going to keep 3 significant figures in our answers. And the first one would be 102 calories. This one would be 1,150 joules. So you can, you know, go back over that with those conversions from like back in Unit 2. Specific heat, also from back in Unit 2, because it's a physical property of all substances. It's this amount of energy needed to raise 1 gram of a substance 1 degree Celsius. So it's for warming and cooling specific heat. Specific heat of water in joules and calories. Okay, so 4.184 joules per gram degree Celsius, 1 calorie per gram degree Celsius. Those values will be important to use in the problems. Now from the table, and this table's in the notes, you can always refer to it to have the specific heats by you, because of course we'd never expect you to memorize them, but you might have to look these up, you know, on a table if it's not provided in the problem. But most of the time it is provided in the problem. Identify the substance with the highest specific heat capacity. Well, that's of course liquid water right here. And then, of course, the lowest is going to be lead. That's 0.129. Also gold here, same value. But those metals are going to have low specific heats. They absorb and release energy very easily without, you know, heating up very quickly. It's cooling down very quickly. Whereas water, you have to give it lots of heat before it's going to change its temperature. It absorbs and releases lots of energy without changing temperature, and that's why it has a high specific heat capacity. So in here, you know, liquid water, lead and gold. Now, the high specific heat of water is due to strong forces of attraction. Obviously, we know that water is polar, has those hydrogen bonding, and that's what allows it to have these unique features and these unique properties. Because of that, you know, it's really strong forces of attraction. We're going to re-talk about forces of attraction, those IMFs, because they really do dictate a lot of the thermochem concepts, in the fact that we're talking about phase changing, overcoming the forces, spreading out the particles. So we'll be revisiting those IMFs later. Calculating heat. Okay, it's Q equals MCAT. That's the formula to use when we're just warming and cooling. We're not phase changing here. We're just warming it up or cooling down. All right, so mass, of course, is in grams. The Q is in is heat, which we usually measure in joules, although some might be calorie problems. Specific heat, joules per gram degree Celsius, and if it's a calorie problem, it would be calories per gram degree Celsius. And of course, temperature change. Final minus initial is the change in the temperature, and that delta T, delta means change of. That's the normal math symbol to be using. So the first example here, we have 40 grams of water heated from 10 to 30 degrees Celsius. How much heat is absorbed in joules? Well, Q equals MCAT. So we plug in our mass, our specific heat. Since it's water, we got that off the table. The final temperature is 30. The initial temperature is 10. We're warming it up. And, you know, the temperature is increasing, so we're adding heat. This is an endothermic process because we're adding in heat, it's absorbing heat. And then, of course, 3 here, 3 and 3 here. We don't base it off of the specific heat, but 3 significant figures in our final answer. Now, with all specific heat questions, you could solve for different variables. You don't have to just solve for Q. In this case, they want you to find the mass of silver. And here, 3.00 times 10 to the third joules. This is going to be your Q value. This is your delta T, the change in temperature, because it's increasing by 35. Now we look at our table for our specific heat of silver. And on the table, it's 0.235 joules per grams degree Celsius. That's where we would find that. Now all I have to do is solve for M using algebra. So, you know, basically divide both sides and get your M, 365 grams. 3 sig figs here, 3 sig figs here. That's what we would use. Now for the heating curve review. Now remember, a heating curve is showing the different phases and the different phase changes. So it is warming at A, where you're warming it up, the particles are vibrating, kinetic energy is increasing as you go up, okay? Then comes the liquid warming is C, so the slopes are going to be where you're warming, and over here the gas warming for E. So A is solid warming, C is the liquid warming, and E is the gas warming. Now B is a phase change, and so is D, because they're the plateaus. The temperature is not changing. The energy is being used to break apart or break the molecules, spreading them out. Now for D, they're going to completely break everything and overcome everything to turn into a gas. That's why it's a much larger plateau, and you need a whole lot more energy than you do for B. B here is melting, okay? So the potential energy is increasing. Positional energy, the molecules are spreading out, going from the solid to liquid. And then, of course, vaporization. You also have potential energy. Now you have gas, which is constant random motion, no intermolecular forces holding the particles together. Once again, you're overcoming all of those intermolecular forces to vaporize. All right, so some of the characteristics of these physical states. Okay, don't worry so much about plasma. We don't really ever talk about it since it's, you know, basically in the sun. But solid molecules are regular repeating patterns. They vibrate in place. They have the stronger IMFs holding them together in that fixed position. Liquids flow easily around each other. They do have some attractive forces, keeping them from, you know, completely falling apart. The liquids, of course, take the shape of their containers. The gas molecules, of course, are in constant random motion, flying around. Pretty much no attractive forces, okay? And as you can say, the increasing, like, kinetic energy is definitely different in these, where the kinetic energy would be lower in the solid. The gas particles have a lot of kinetic energy. Here's some other graphs. This one goes through the phase changes with their names. So you can look at sublimation versus deposition, vaporization, condensation. Now fusion is another name for melting, by the way, and freezing. I put this graph in here too because the definite shape and definite volume of the solid, indefinite shape but definite volume of the liquid, because the particles are still closely packed. And in a gas that's indefinite shape, indefinite volume, we say the gas takes the shape of the container. The gas fills the container completely, whereas the liquid takes the shape of the container. The gas fills it completely if it's a closed container. So it will, like, just bounce off the walls of the container. This diagram shows you as temperature increases, you know, you can go from solid to liquid to gas. The molecular motions too, kinetic energy is increasing, solid, liquid to gas. However, the molecular interactions, now this is where we're talking about those IMFs. IMFs are stronger for the solid than they are from the liquid versus the gas, because the liquid has more movement. Solid, they can only vibrate in place. So you have the stronger intermolecular attractions holding the particles together. They do have kinetic energy, though. They do vibrate, and so the solid does, you know, even those particles still have energy. So phase changes, molar heat of vaporization. Now we're going to get into using the mole here. Takes 1 mole, you know, to go from a liquid to a gas. That's molar heat of vaporization. We call it delta H vape, like that. So it's also the amount needed to release when condensing, because remember, vaporizing liquid to gas, okay, that's going to be endothermic, where you add the energy. But if we're going from gas to liquid, it's releasing the energy, so that's going to be exo. And all you basically do is, it's positive delta H if we are vaporizing. It's basically negative delta H if we are condensing. It's the same magnitude, it's just the opposite sign, and the sign is used for the direction. Is the energy being absorbed or is the energy being released? Now fusion, heat of fusion, so we say delta H fusion. Okay, solid to a liquid, all right, and it's positive if we are melting, and that of course is also endothermic. But if we are going the opposite way and freezing or crystallizing, that's another word for freezing, it would be a negative, oops, don't know why it does that, where it makes that big huge line, but let's erase that. And we would get our delta H of fusion, but it would be a negative. Since you are releasing the energy, and freezing is an exothermic process, releasing energy versus absorbing energy. Now they will use your tables, of course, in the handout. This is in the notes that you can print out or you can refer to. And we don't take the SOL anymore, but they are usually given in the problem. They would never expect you to memorize any of these, so keep that in mind. 40.7, 6.01, vaporization versus fusion. You can tell between both, all of these, that the vaporization number is smaller. I mean, the fusion number is much smaller than the vaporization. Once again, you have to overcome all of the forces to change it from a liquid to gas. So that's why these numbers are much larger, okay? Specifically larger. So we're going to work a few problems. I'm going to show you a couple of how to do this where you are figuring out the amount of heat to phase change. Q equals MCAT is warming and cooling. So now we're going to look at phase changing. It's a different type of calculation. So set up a T-chart. You need to change your grams to moles. And then you use the correct delta H, whether it's vaporization or fusion, from the chart. So here, if I have 125 grams of ice, which is water, and I am going to melt it, well, first thing I need to do is change my grams to moles, because the heat of fusion is kilojoules per 1 mole. That is the for water off of the chart there. So 1 mole, and we know the molar mass of water is 1802. You can refer to your periodic table for that though. But this is where it gets a little tricky. So now the moles go down here and the kilojoules go up here. So we're going to use this conversion. 6.01 kilojoules equals 1 mole in terms of melting of ice. Now everything cancels, the moles cancel, and we can calculate and get our value of heat needed to melt 125 grams of ice. And since we have 3 significant figures here, we would round it to 3 significant figures over here. So I set up the T-chart as such, like so, and you can go ahead and calculate. Now this is for boiling. We're boiling, so in this case we want the heat of vaporization number, which I believe for water happens to be 40.7 kilojoules per 1 mole off of the table. So I'd still set it up exactly the same way. I'm going to change my grams of water to moles of water first, equals 1 mole of water. And then I would diagonal down my moles, put my kilojoules up here, put in my heat of vaporization, and I would be able to calculate the amount needed to vaporize 125 grams of water. And that calculation, of course, as you can see, is a higher number than the fusion one. Once again, overcoming all of those intermolecular forces holding the particles together. Now this one's very similar, same deal, except for different substance. We have ammonia, remember NH3, okay, at its freezing point. So really, you're doing heat of fusion, but it's going the opposite direction. Instead, we're releasing. Now you can even say, the word released, or you can use the negative sign to dictate which direction the heat is going. If it's absorbing, it's positive. If it's releasing, it's negative. So here, got this number off chart for the heat of fusion. So I would say, 81.0 kilojoules is released in order to freeze ammonia, okay, at its freezing point. But ammonia is NH3, so this value is its molar mass off the periodic table. You just add them up. Same kind of setup here. This one is the interesting one where you have to work backwards. So you would start with the heat over here. This is your given information. And of course, this is ethanol, so it's what? C2H5OH. And you would put the kilojoules down here equaling 1 mole, because the heat of vaporization, or the delta H, vape, is going to be a measurement in kilojoules per mole. I think it's 30 something off the table. I don't remember, but we would put the 1 here, of course, and then like you would do 1 mole of your methanol equals the, I think it's 46.08 grams of methanol off the periodic table. You would calculate that too. This number I don't exactly remember off the table, but here it'll show you in the next step of the problem. But the kilojoules now diagonal down. You go to moles first, then you diagonal down the moles, and you can go to grams, and you can work backwards using the T-chart. Yes, it's 38.6 kilojoules equals 1 mole to vaporize ammonia. Okay, 3 sig figs over here because we start with 3 over here. Just working backwards. Diagonal down kilojoules, go to moles, because the heat of vaporization, remember for ammonia, that is going to be 38.6 kilojoules per every 1 mole. So we use the conversion factor. Now, more heating curve review, which equation to use along the points. So if we are warming something like A, C, and E, these are all going to be Q equals MCATs because we're just warming it degrees Celsius, a certain amount of grams. But if we are melting, we're going to do the moles times the heat of fusion, and a lot of times they give you grams to start with, so you have to change it to moles and then multiply it by the heat of fusion. So liquid warming, still MCAT. Heat, this one is vaporization, so now it's moles times heat of vaporization. And then, of course, if you're warming the gas, it's going to be an MCAT. So along the heating curve, you're going to use these different equations. Now, this one's really more like a T-chart because we usually start with grams, like I said, and then we have to work to the kilojoules. But let me show you a problem like this, where we're starting with 23 grams of ice, and okay, the negative sign didn't carry over, but I'll put it here. So we're starting at negative 11 degrees Celsius, and we want to know how much energy it takes to turn it into liquid water that has a temperature of 49.5 degrees Celsius. So really, we're starting somewhere down here on the curve. We have to warm, oh, I hate it when it does that. Erase that. All right. So we need to warm it right here up to 0. Then we need to melt it across, and then we need to warm it again to get it all the way up here to that 49.5 degrees. So there is actually 3 steps. We have step 1, step 2, step 3. We have to warm it to the phase change, then we have to phase change it, that's step 2, and then we have to warm it again to get it to a liquid at 49.5 degrees Celsius. Now, in these problems, of course, they give you all of the data here in a table to use. Heat of fusion, heat of vaporization, the specific heat of the solid form, the liquid form, and the gaseous form, because they are different values. So ice has a different specific heat than liquid water, which has a different specific than the water vapor. Heat of vaporization and the heat of fusion numbers are also provided here. Although in this case, we're only going to be melting, so we're going to need the heat of fusion. We're going to be using the solid because we're down here in the solid, so we're going to need that one. And then, of course, we're also going to need to warm it, so we're going to need the specific heat of the liquid. We're not up here in the gas stuff, so we don't need the vaporization or the specific heat of the gas. So step 1 first is warming it to 0 like we wanted to. So 23 grams, the specific heat of the solid. Now, the final temperature, because we're warming it up to the phase change, this is your final temperature, this is your initial temperature. So we're subtracting the negative number. We end up with this amount of joules in order to do that. Now we're here, we're going to melt it. So the second step is the melting part. So changing the 23 grams into moles, use the heat of fusion number here. And notice this is in kilojoules, whereas this one's in joules. So we're going to eventually have to convert one to the other. Now we've melted it. So now we're here, and now we need to warm it up to the 49 degrees somewhere here. So that's going to take one more Q equals MCAT. Except for now, our starting temperature is 0. That's our initial temperature, and our ending temperature happens to be 49.5. So watch where you're starting for your temperature, watch where you're ending on the curve as you're going up the curve. And that takes, you know, this many joules. We're using the specific heat of the liquid. The initial temperature of the liquid is at 0 because that's where we left off the melting part. Now, once we have all of these calculations done, as seen here, now we can just add, you know, convert them to kilojoules and add them up. So take your joules, divide them by 1,000. So this one was already in kilojoules, but we had to make that kilojoules, and we had to change that one into kilojoules. And then we know how many kilojoules was needed to take the piece of ice from negative 11 degrees Celsius and get it changed into liquid water that was at a temperature of 49.5 degrees Celsius. So multi-step here, this is definitely the honors level question. Okay, and I think I gave you one for practice because, you know, once you follow the curve and do it, it's really not hard. Just, you know, if you're warming, make sure you're using MCAT. If you're phase changing, make sure you're using the fusion or vaporization. Now for phase diagrams. We did not go over these before. We're going to be looking at triple point stuff and the different phases represented by pressure and temperature here. Now, before we get into this particular, you know, mysterious compound X diagram I want to look at, this one provides you all of the markings on the triple point curve. Triple points here, critical points up here, and these are all the this line right here is all of the different melting and freezings at different pressures and different temperatures. This line is the vaporization condensation line. Sorry, I didn't draw that very well, but here, let me try again, sticking on the line a little bit better. This is where vaporizing and condensing occurs at different pressures and temperatures. And then, of course, this is between the solid and the gas over here. So sublimation deposition is this line right here and takes place. Now, at the triple point, all three phases are occurring at once. At the critical point, though, up here is where you can't really tell if it's liquid or gas anymore because it's super hot, so the particles are moving really fast and wanting to spread out. But you're at high pressures, so they're like wanting to condense too. So it's kind of an in-between phase. We call it a supercritical fluid. Not that important, not really, but notice at this part, that's where the line stops, is because you can't really tell whether it's gas or liquid at that point. But I do want to show you the triple point of cyclohexane, so I think I have to reshare here, so give me a second. All right, so in the flask is cyclohexane, and they're using a vacuum to lower the pressure right now to get it to the triple point, you know, and keep it at the right temperature and the pressure's right at the triple point. Now it's turning into a solid. And as you'll see, the three phases are going to start to appear all at once. It's just going to keep changing back and forth between the three phases. Okay, so we just saw a bubble, and it's going to bubble out and liquefy. Here we can see some more. There we go, bubbling out, liquefying. So all three phases are in an equilibrium at the triple point. So this is the triple point of cyclohexane. It's freezing again. Now it's about to go liquid and gas again. So it just keeps alternating and creating the three different phases at that pressure and temperature. So that's kind of a nice little demonstration of, but the triple points are hard to attain because you need to really lower the pressure for a lot of these substances. PowerPoint. All right. So in order to get to that triple point, usually you have to use a vacuum to suck out the pressure, or the extra stuff to lower the pressure right here to get it to that point. Temperature is easier to manipulate. All right, so using the Phase diagrams, these are simple problems. It's reading the graph. So one of the quizzes that you're going to have on Blackboard is going to be reading the graphs. So here's our triple point, you know, basically looking there. So let's determine the triple point. Okay, well, that's about 350. This is at 50 ATM, you know, not hard, just read the graph. What will all three phases coexist? That's another way of asking for the triple point. So 350 degrees and 50 ATM. Now, what phase changes occurs when you heat it from 100 to 400 at 40 ATM? Well, here's the 100. We're going to go to 400. So what phase change occurred? We went from solid to gas. That would be sublimation. Okay, so check that out. Very easy, simple, read the graph kind of deal. Here, what phase changes occur when it's heated from 100 to 450 at 70. So we're here at 70, we're at 100. We're going to 450, which is right about here. So as you can see, going up there, you are going from solid to liquid, and that would be melting. What phase occurs when you're cooling it from 700, here we're at 60, we're going to cool it to 500. And that's going to be gas to liquid, so that's condensation. And then, of course, occurs what phase changes occur when you're going from 700 to 300 at 70. So 700 all the way over here to 300. Well, you have two phase changes. You have the condensation and the freezing, both occurring. So pretty simple to read the phase diagram, triple point curve. Just a review real quick of shapes and polarity, although I won't be asking a lot about this. This helps us guide into intermolecular force strength, which you need to know in order to, you know, compare substances of different vapor pressures and boiling points. All right, so going back over nonpolar versus polar. Nonpolar are formed when there's equal sharing. Polar is formed when there's unequal sharing of electrons. Determining the molecular polarity, nonpolar molecules equal sharing. Symmetric, all the dipole moments cancel out. So even though the fluorines are highly electronegative and pulling on those electrons, it's all in equal directions off the central atom. So that's why it'd be symmetric and nonpolar. Here, polar molecules have an unequal sharing. Okay, they have the electronegativity differences, but here the dipole moments sorry, I don't know why it does that, but let me try again. The dipole moment goes towards the oxygens. The oxygen has the partial negative side. The hydrogens are the partial positives. Stop doing that. All right. Come on. Partial positives over here, partial positive. So it's a permanent dipole. And so in this particular case, there's an unequal sharing. Most of the electrons spend their time around oxygen, and it's asymmetric, so this one would be considered polar. CO also, the dipole moment goes towards the oxygen, the more electronegative element, and therefore this side's partially negative, this side's partially positive, creating a dipole as well, which is a polar molecule. So remembering shapes and determining if it's polar or nonpolar, well, of course, ammonia has this lone pair, so the dipole moments all go towards the nitrogen, being the more electronegative element, has a larger electronegativity difference. This is going to be pyramidal shape, though, three things attached, one lone pair. This one's definitely going to be polar. Over here, fluorine to fluorine, the electronegativity difference is going to be 0. It's a linear molecule, and they're the same atoms, so obviously it's nonpolar. This is kind of a little bit of a review of shapes and polarity because we need that to determine the IMFs involved. Now here, you know, I'm just going to go ahead and go over these real quick. Hydrogen chloride is linear but polar because the dipole moment goes towards the chlorine, chlorine being more electronegative. The bent shape one, we already kind of did this with water. They go towards the oxygens. But if you're looking at our methane over here, methane, this one is tetrahedral. All the ligands are the same. There isn't really dipole moments because the electronegativity difference between carbon and hydrogen is 0.4. It's like 2.5 minus 2.1. So there's just no nonpolar bonds in there. So we would say that is nonpolar. Now intermolecular forces, recalling these here. Difference in properties, these attractive forces between molecules and compounds, we call them IMFs. But intramolecular forces are ionic covalent metallic bonds. They're the actual bonds within. They are not between, they are within the molecule. And so our identical molecules, the intermolecular forces, attract to, like water attracting other water molecules in a drop, that would be considered intermolecular forces. The bond between the hydrogen and the oxygen, though, that's sharing electrons, that is covalent and intra or within. So inter between, many physical properties due to these IMFs. So if we're looking here at this example, this guy right here is an intra because that's the covalent bond. The dotted line, though, which is not as strong, is the intermolecular force because it's between the two water molecules. Now, the first type of force is London dispersion forces. This is the temporary dipole ones. That's because of the electron cloud being forced over. So nonpolar exhibit London dispersion forces, and they are the weakest. So basically coming in contact near another electron cloud shifts it over, and the nuclei of this one attracting those electrons shifts it over. So you have these temporary dipoles, the positive, negatives attracting, Coulombic attractions. But this goes for nonpolar and anything with an electron, even electron cloud, even noble gases have London dispersion forces. Polar molecules exhibit dipole-dipole interactions. Okay, oops, hold on, let me go back to that. I went too fast. So here we have our permanent dipole with the dipole moment. So positive, negative attraction here, okay, between the two hydrogen chloride molecules. They line themselves oppositely. This is slightly stronger. Now, of course, the hydrogen chloride also possesses London dispersion forces because of the cloud. London dispersion forces, of course, increase with the amount of electrons because it's a more polarizable cloud. But this one also has the added force of the dipole-dipoles because it's a permanent dipole. Now the hydrogen bonds, which are stronger than dipole-dipole forces. Now water has all three. Water has London dispersion forces, it has the dipole-dipole interactions, and it has the hydrogen bond because it's uniquely got the huge electronegativity difference between the hydrogen and these different atoms. H bond, HF, HO, or HN can exhibit hydrogen bonding, where you have that extra added little 5 times stronger force. So it's really dipole-dipole interactions, the same thing, but it has the extra added strength due to the huge electronegativity difference between hydrogen and those atoms, HF, HO, or HN. That also gives water its very significantly unique properties: high surface tension, high heat of vaporization, high specific heat. Why? Because it's very adhesive to itself. It sticks to itself. Or cohesive. Cohesive is sticking to itself. Adhesive, sticking to something else. It is adhesive to lots of polar things as well, but it is very cohesive in the fact that it sticks to itself because of those forces, those hydrogen bond forces. Now here's just going over some things, so we'll just talk about them, like tetrahedral shape. All the ligands are the same, nonpolar. So the only thing it's going to exhibit in terms of forces are LDFs. Whereas the bent molecule is polar, but there's no hydrogen in here, so these are just dipole-dipole interactions. And then, of course, this is a pyramidal shape one, also no hydrogen. The polar as well, so dipole-dipole interactions. The HF, though, is a linear, but it does have the hydrogen bonding because it's H to F, huge electronegativity difference, huge dipole moment going towards the fluorine. So this is a huge partial negative, huge partial positive. Now, the stronger the force is, the more energy needed to overcome or break the forces. So we have to overcome them to melt a little bit. We have to completely overcome them to boil. So this is where this comes into play with the heat and thermo. So looking at vapor pressure. Vapor pressure data. Vapor pressure is the gas that stays on the top layer of the liquid. It's in a closed container, it's in equilibrium, so as it's condensing, it's also evaporating, and it forms this thin layer of gas on top. Now this one has less gas over here, so we'd say it has a lower vapor pressure than this one over here that has a higher vapor pressure. Okay, so keep in mind that, if it has a higher vapor pressure, that means these attractive forces between the liquid phase and the gas phase is not as strong, so it's not holding on to the molecules. Over here, where it has a lower vapor pressure, that means the strength of the forces is higher because it's holding on to them more tightly. So we use vapor pressure curves. It's temperature versus the vapor pressure, okay? And at 1 atmosphere, of course, that's standard pressure. So that's the pressure at sea level, right? This is what we would consider to be like the normal boiling point. At standard pressure, what is the boiling point of the substance? In this case, this would be water because it's 100 degrees, so I would know that. And 1 atm is as standard pressure, so is 101.3 kPa, and 760 torr or millimeters of mercury is also considered standard pressure. Standard pressure at sea level. Now, reading the vapor pressure curve, what you need to look at, different intermolecular forces for different vapor pressures. Diethyl ether has a normal boiling point, which is at sea level at 760 torr. That one is 34.6 degrees Celsius. Compare that to water at 100 degrees at the same pressure. Obviously, the diethyl ether has weaker forces, and it's easier to overcome them to make it turn into a gas than water. Water, you need a lot more energy, so you have to increase the temperature in order to get it to boil. And in order to get it to boil or vaporize, the atmospheric pressure has to equal the vapor pressure of the substance. That's right here. Liquid boils when the atmospheric pressure equals the vapor pressure. Now, and that's another thing to think about, like the mountains in Colorado. Why is it easier to boil stuff up there? Because the atmospheric pressure is lower. So you're up in the mountains, it's thinner up there, so you don't need to heat it as much in order to boil substances in the mountains. Stronger, lower vapor pressure, higher boiling point. Those things are all relatable. From this graph, we can see that water has the strongest IMF, followed by ethanol, and then diethyl ether. We're just looking at the ones on the curve, not caring about that one over there. So water has the strongest ethyl alcohol or ethanols in the middle, and then diethyl ether. We could look at individual forces on these as well and figure out, of course, water has hydrogen bonding, and the ethyl alcohol does too, but the diethyl ether is just dipole-dipole interactions. All right, so you have to be able to read the vapor pressure curves, not too hard. It's basically just looking at on the curve. So it says, at 50 degrees, we would go here and we would, what is the vapor pressure at 50 degrees? Well, that's 70 kPa. And if we wanted to know the vapor pressure of water at 70 degrees, we would just go up here to the water line, and that would be 30 kPa. Now, all the normal boiling points would be up here at the standard pressure line. Okay, so 100, this one's about, what, 75, and this one's just slightly over 60 maybe, for the CHCl3. Reading the graphs, not too hard. All right, so don't forget that, this is standard pressure here. That's where you're looking for the normal boiling points. Heat transfer and heat of reaction. So a couple of things to go over real quickly about this. So you'll have one problem to do here. The heat transfers from the warmer object to the colder object. So Q equals Q here. So that means that MCAT can equal MCAT because Q equals MCAT. But what you need to know is one object is colder than the other. So the losing side, one losing heat gets the negative. The object gaining the heat gets the positive because it's an equal magnitude of transfer here. So if we have a gold block with a mass of 125 that's cooled and dropped into a beaker containing 200 grams of water at 25 degrees Celsius, the final temperature of the water is 22 degrees. What is the initial temperature of the gold block? They tell us the specific heat of the gold here. Now, basically what we're going to see here is that the water is losing heat because it's going from 25 degrees Celsius to 22. And it tells us that the gold is cold, so it's going to gain heat, and the water is going to exchange heat with the gold. So the gold side gets the positive because the gold's going to gain heat, the water is going to lose heat. Now all you have to do is plug in the numbers. So mass of the water, specific heat of the water, final temperature of the water, initial temperature of the water. Over here, don't forget your negative sign over here as well, because that's the losing side, losing heat. The mass of the gold, the specific heat of the gold. The final temperature is the same as water because the gold is sitting in the water beaker now. So they are at the same final temperature. So T final would be the same for both objects, and then you can calculate T initial. Then it becomes just a simple calculation algebra game, solve for Ti over here. And you end up getting the initial temperature of the gold is always very cold, but remember the gold has a very small specific heat, so, and the water has a high specific heat, so to get that water to change temperature a lot, you know, it's going to have to be a lot of coldness, and it only went down 3 degrees, went from 25 to 22. So took a lot of a very cold little small piece of gold in order to do that. The last thing I want to talk about is heat of reaction. Oh, yeah, this part's wrong too. I forgot to change it. But this is supposed to be exo here. Negative values are always exo. Positive values are always endo. And we're talking about delta H of reaction. So this is actually taking place in a reaction. So the heat is a product, it's going to be exothermic. If the heat is a reactant, it's going to be endothermic. So far, we've been just talking about phase changing and warming and cooling things. Now we're going to actually react them. And when we do a reaction, we have bonds breaking, bonds forming, so there is an exchange of energy, and they can be endo and exothermic processes as well. So if you're looking at the example down here, the energy gain endo is positive. That's what's shown here, that we have a positive delta H for this reaction, so we would label it endo. Energy loss, of course, if the heat is on the product side, okay, this could also be written as a negative delta H, like so. And that would be also a good way to write it if it was written as a negative delta H, okay? And that would be exo there identifying the information. One example problem, and then I'll be done. Calculate the heat released when 17.1 grams of iron 3 oxide happens to be produced according to this following reaction. So this is the delta H value, which is really negative 560.4 kilojoules because it's on the product side. So I know this is exothermic. It is releasing energy. It is a simple set it up, you know, like a T-chart problem, grams Fe2O3, grams Fe2O3 to moles, like so. And then we use our, you know, heat over here, but there are 2 moles in the equation. So this is 1 mole Fe2O3. So this is going to be 2 moles down here, Fe2O3, and then to our energy for the reaction goes up here. Now I can put it in as a negative, or I can say it's being released. Those are your 2 choices. So this amount released, you can say that, or you could say negative 30 kilojoules, because we know that's how much is being released when we produce 17.1 grams of the product over here. So balanced equation using the mole ratios here, 4, 1, 2. We could really calculate it for any of these substances if we wanted to, but to produce 17.1 grams of the product, this is how much energy gets released, 30. So keep that in mind. That's obviously not close to 2 moles. 2 moles would equal 560.4, and 17.1 grams is definitely way less than that. So keep that in mind when you're doing the reaction problems. Look at your balanced equation, look at the moles of the substance. That's equivalent to the delta H of the reaction.